Look up at the night sky for a moment and really think about what you're seeing. For thousands of years, people stared at those scattered points of light and filled the darkness with stories of gods, spirits, and cosmic battles. Today we tell a different story, one grounded not in myth but in geometry, physics, and the strange behavior of space itself. It is the story of how the universe evolved, and it begins not with a simple explosion in empty space, but with a transformation of space and time on the deepest level imaginable. The image most people carry in their minds is of a gigantic blast that hurled galaxies outward into a pre-existing void, like fragments from a cosmic bomb. It's dramatic, but it's also misleading. A better picture is to imagine a vast loaf of raisin bread rising in an oven. Each raisin represents a galaxy. As the dough expands, every raisin moves away from every other one. None of them sits at the center, and no direction is special. The expansion happens everywhere at once because the dough itself is stretching. In the same way, the universe isn't expanding into space. Space itself is expanding, creating more distance between galaxies without needing a central starting point. This realization emerged in the early 20th century when astronomers began measuring the light from distant galaxies. Edwin Hubble and others noticed something remarkable. The light from faraway galaxies appeared shifted toward redder wavelengths. This redshift works much like the change in pitch of a passing train horn. When the train moves away, the sound stretches and deepens. Light behaves similarly. If a galaxy is receding, its light stretches toward the red end of the spectrum. Even more striking was the pattern that emerged. The farther away a galaxy was, the faster it seemed to be moving away from us. Plotting this relationship produced a straight line. Distance and velocity were directly proportional. The constant that defines this relationship, now called the Hubble constant, tells us how quickly the universe is expanding. If you mentally run this expansion backward, the picture becomes dramatic. Galaxies draw closer together. The universe grows denser, and temperatures rise. Continue that process far enough, and you arrive at a state of extreme heat and density about 13.8 billion years ago. This is what we call the hot Big Bang. Notice the phrasing carefully. It describes a phase in the universe's history, not necessarily the absolute beginning of everything. It marks the earliest point where our current theories can describe conditions with confidence. The theory that makes sense of this cosmic expansion is Einstein's general relativity. In this framework, gravity is not a force pulling objects through space. Instead, mass and energy shape the geometry of space-time itself. Imagine stretching a rubber sheet tight and placing a heavy ball in the center. The sheet bends, and smaller objects roll toward the dip, not because they are pulled directly, but because they follow the curved surface. On the scale of the universe, matter bends space-time, and that curvature guides how everything moves. When mathematicians like Alexander Friedman applied Einstein's equations to a universe filled evenly with matter, they discovered something surprising. The equations naturally allowed for expansion or contraction. The universe didn't have to be static. For a time, Einstein preferred the idea of an unchanging cosmos, and even modified his equations to allow it. But observations soon forced a different conclusion. The universe was clearly expanding. This discovery sparked a major debate in 20th century cosmology. One camp supported the hot Big Bang model, arguing that the universe began in a hot, dense state and has been cooling ever since. The other proposed the steady-state theory, which suggested that the universe has always existed in roughly the same form, with new matter appearing to keep its density constant as space expands. The decisive evidence arrived unexpectedly in 1965. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a sensitive antenna, trying to eliminate a persistent hiss that seemed to come from every direction. They checked the equipment, cleaned it, even removed nesting pigeons, but the noise remained. What they had stumbled upon was not interference at all. It was the faint glow left over from the early universe itself, the cosmic microwave background. This radiation is the cooled remnant of a time when the universe was hot, dense, and filled with glowing plasma. As space expanded, that light stretched and cooled until it became microwave radiation, now bathing the cosmos almost uniformly. its discovery was decisive. It matched the predictions of the hot Big Bang model perfectly and effectively ended the steady-state theory. We were no longer just theorizing about the early universe. We were detecting its afterglow directly. Yet this success introduced new mysteries. The cosmic microwave background is incredibly smooth, almost the same temperature everywhere. That uniformity suggests that the early universe was remarkably even and orderly, but not perfectly so. Tiny fluctuations, only millionths of a degree in difference, were later mapped with extraordinary precision. Those small variations mattered enormously. They were the seeds from which gravity would later build galaxies, clusters, and the vast cosmic web we see today. Another puzzle comes from thermodynamics. The second law tells us that entropy, a measure of disorder, always increases. Systems naturally move from order to chaos. An intact egg can scramble, but scrambled eggs never reassemble themselves. This direction defines the arrow of time. Yet the early universe appears to have been in an extremely low entropy state, unusually smooth and organized. That raises a deep question. Why did the universe begin in such a special condition, so ordered compared to what the laws of physics would normally allow? As we push our mathematical descriptions further back toward the earliest moments, we run into a problem. General relativity predicts a singularity, a point where density and curvature become infinite, and the equations stop working. This is the classical Big Bang singularity. Most physicists interpret it not as a literal physical event, but as a sign that our theories are incomplete. At such extreme scales, quantum effects must become important, and our current models struggle to unite gravity with quantum mechanics. At the smallest conceivable scale, known as the Planck scale, spacetime may no longer be smooth. Instead, it could behave like a frothy, fluctuating structure, where the usual ideas of distance, time, and even causality become uncertain. If that picture is correct, then the hot Big Bang might not represent a true beginning, but rather a transition from some earlier quantum state of the universe. This possibility has inspired some of the most ambitious ideas in modern cosmology. One of the most influential is cosmic inflation. According to this theory, shortly after the earliest moment we can describe, the universe underwent a brief but incredibly rapid expansion. Space itself expanded exponentially, driven by a form of energy inherent to the vacuum. This burst of growth would have smoothed out irregularities, explaining why the cosmic microwave background looks so uniform. At the same time, tiny quantum fluctuations would have been stretched to enormous scales, becoming the initial patterns that later formed galaxies. Inflation offers elegant solutions to several problems at once. It explains the large-scale flatness of the universe, its uniform temperature, and the origin of structure. While the exact mechanism behind inflation remains uncertain, observational evidence continues to support the idea that something very much like it occurred. Beyond inflation, theories become even more speculative but also more fascinating. Some suggest the universe could have arisen from a quantum fluctuation in a primordial state. Others propose that the cosmos undergoes endless cycles of collapse and rebirth, a big bounce rather than a one-time beginning. In such models, a previous universe might have contracted into a dense phase before expanding again into the one we inhabit. And then there are ideas that challenge the very concept of a beginning. Some physicists argue that asking what happened before the Big Bang may be like asking what lies north of the North Pole. The question itself might lose meaning at the earliest moments. One proposal along these lines is the no-boundary model developed by James Hartle and Stephen Hawking. In this view, time behaves more like a spatial dimension near the origin of the universe. Instead of a sharp starting point, the universe could be finite yet without an edge, much like the surface of a sphere. There is no boundary where time suddenly begins. It simply curves smoothly into existence. What makes this perspective powerful is that it removes the need for a singular moment of creation. The universe does not explode into being from nothing in a single instant. Instead, the geometry of space-time evolves continuously, guided by quantum rules that replace classical ones at extreme scales. Whether this model is correct remains uncertain, but it illustrates how modern physics is rethinking the earliest stages of cosmic history. Despite these deep uncertainties about the origin, one remarkable achievement stands out. From a fraction of a second after the hot dense phase began, we can trace the universe's evolution with impressive accuracy. The formation of the first nuclei, the release of the cosmic microwave background, the gradual clumping of matter into galaxies, stars, and planets, all follow from well-tested physical principles. The hot Big Bang framework describes this unfolding story with extraordinary success. What remains unresolved is the deeper question of what triggered that hot phase, or what preceded it. This is where cosmology meets quantum gravity, and where our understanding is still incomplete. It's a frontier where the largest structures in existence intersect with the smallest scales imaginable. Solving it requires uniting general relativity, which governs gravity and the structure of space-time, with quantum mechanics, which describes the behavior of matter and energy at microscopic scales. We are fortunate to live in a time when this investigation is no longer purely theoretical. Observations continue to provide new clues. The cosmic microwave background remains our oldest observable signal, a kind of baby picture of the universe. By studying its temperature variations with ever greater precision, scientists can test models of inflation and probe conditions that existed when the universe was only a tiny fraction of a second old. Future measurements may push this exploration even further. Gravitational waves generated during the earliest moments could carry information from epochs otherwise hidden from view. Mapping the distribution of galaxies across enormous distances reveals how matter has evolved over billions of years, offering indirect evidence about the physics of the early cosmos. Each new observation refines our models and occasionally forces us to rethink them entirely. This ongoing process reveals something important about science itself. The goal is not to settle on a final, comforting explanation that ends all questions. Instead, progress comes from continually testing ideas, discarding those that fail, and building deeper frameworks that explain more of what we observe. Every answer tends to expose new layers of mystery. That pattern is especially clear in cosmology. Discovering that the universe expands led to the Big Bang model. Finding the cosmic microwave background confirmed it, but also raised questions about initial conditions and entropy. Inflation may explain several puzzles, yet it opens new ones about its mechanism and origin. The deeper we look, the more the universe challenges us to think beyond our previous assumptions. This cycle of curiosity and revision is not a weakness. It is what connects us to the cosmos. By trying to understand the universe's history, we are participating in a process that spans billions of years, linking human thought to the evolution of galaxies, stars, and ultimately the atoms that make us. And this connection becomes even more meaningful when we consider what lies ahead. The universe is not a static backdrop, but an evolving system whose future is shaped by the same expansion that defined its past. Observations over the last few decades have revealed something unexpected. Not only is the universe expanding, that expansion is accelerating. Galaxies are drifting apart faster over time, as if some hidden influence is pushing space outward. This discovery emerged from careful measurements of distant supernovae in the late 20th century. Astronomers expected the expansion to slow down due to gravity's pull. Instead, the data showed the opposite. The expansion was speeding up. To explain this, scientists introduced the idea of dark energy, a mysterious component that appears to permeate space itself and drives cosmic acceleration. Dark energy is not yet fully understood, but its effects are measurable. It now dominates the large-scale behavior of the universe. If it continues to act as it does today, the cosmos will grow increasingly empty as galaxies drift beyond one another's observable horizons. In the distant future, observers in any given galaxy might see only their local cluster, with the rest of the universe effectively hidden by expansion. The night sky, once filled with countless galaxies, would gradually darken. This future highlights how deeply cosmic expansion shapes everything we observe. The same stretching of space-time that carried galaxies apart after the hot Big Bang now determines the long-term fate of the universe. Understanding its origin is therefore not just about the past, but about the entire cosmic timeline. Returning to the early universe, one of the most important lessons we have learned is that structure grows from tiny beginnings. The slight temperature variations in the cosmic microwave background represented minuscule density differences. Over billions of years, gravity amplified those differences. Regions slightly denser than average attracted more matter, eventually forming galaxies and clusters. Without those early fluctuations, the universe might have remained a smooth, featureless sea of particles. Inflation provides a compelling explanation for the origin of those fluctuations. Quantum uncertainty at microscopic scales, normally confined to the realm of particles, would have been stretched by inflation into macroscopic variations across space. In this sense, the galaxies we see today may ultimately trace their origins to quantum events in the universe's earliest fraction of a second. The largest structures in existence could be the amplified echoes of the smallest physical processes. This idea beautifully links the quantum and the cosmic. It suggests that the universe's vast structure is not separate from quantum physics, but emerges from it. The same uncertainty principle that governs subatomic particles may have shaped the distribution of galaxies across billions of light years. Even with this progress, many questions remain. We still do not know the exact nature of dark energy. We do not fully understand how inflation began or ended, and we have yet to unify gravity with quantum mechanics into a single theory that can describe the earliest moments with confidence. These open questions define the frontier of modern cosmology. What makes this pursuit remarkable is that it is grounded in observation. We are not merely speculating about unseen realms. Every new telescope, detector, and experiment expands our reach. From mapping background radiation to detecting gravitational waves from merging black holes, each discovery adds another piece to the puzzle of cosmic history. This process reminds us that the story of the universe is not finished. It continues to unfold as we gather data and refine our theories. Our current understanding may one day be replaced by a deeper framework, just as Newton's ideas were expanded by Einstein's. Science advances by questioning itself, and as we push toward those deeper insights, we begin to appreciate how extraordinary it is that the universe can be understood at all. From a species that once mapped the sky with myths and constellations, we have reached a point where we can trace the universe's history across billions of years using mathematics, observation, and careful reasoning. The light we capture in our telescopes today began its journey long before Earth existed, carrying with it information about the state of the cosmos in distant eras. By decoding that light, we reconstruct a story that stretches from the hot early universe to the intricate web of galaxies we see now. What makes this story powerful is not that it offers a final answer, but that it keeps expanding. Each discovery reshapes our understanding. The hot Big Bang explains the universe's evolution after its earliest measurable phase, yet it leaves open the question of what, if anything, came before. Inflation may describe how the universe achieved its large-scale uniformity, but it prompts new questions about the physics driving it. Dark energy explains the accelerating expansion, but its nature remains one of the deepest mysteries in science. This is not a failure of our models. It is the natural outcome of pushing knowledge forward. Every time we resolve one layer of uncertainty, another appears beneath it. That pattern mirrors the expansion of the universe itself. Understanding grows outward, revealing new horizons rather than closing them. In this sense, cosmology is not just about distant galaxies or abstract equations. It is about our place in a larger narrative. The atoms in our bodies were forged in stars that formed from clouds shaped by early cosmic fluctuations. The same laws that govern the young universe govern the chemistry of life today. When we study cosmic history, we are also studying the conditions that made our existence possible. The cosmic microwave background, faint though it is, stands as our oldest observable artifact, a snapshot of the universe when it was only hundreds of thousands of years old. Future measurements may push that boundary even further back. Gravitational waves from the earliest epochs or deeper maps of cosmic structure could offer clues about inflation or the quantum nature of spacetime. Each new observation extends our reach closer to the unknown. But perhaps the most important lesson is philosophical rather than technical. The universe does not reveal itself all at once. It invites investigation, rewards curiosity, and resists simple answers. The search for understanding is ongoing, and that ongoing effort is part of what connects us to the cosmos. We often look up at the night sky and see distance, silence, and darkness. Yet what we are really seeing is history unfolding across time, light traveling immense distances to tell us where it has been. The sky is not just a backdrop. It is a record of transformation, a reminder that everything we observe is part of a process still in motion. So the story of the universe's evolution is not a tale with a neat beginning and end. It is an unfolding investigation, a conversation between observation and theory that continues with each generation. We may never reach a final explanation of origin, but the pursuit itself deepens our understanding of reality, and that pursuit is what truly matters. Every question we ask about the cosmos is also a question about ourselves, about where we came from, and how we fit into the vast structure of existence. In seeking those answers, we participate in the same unfolding story we are trying to understand. If this journey through cosmic history sparked your curiosity even a little, hold on to that feeling. The universe is still revealing its secrets, and the next breakthrough could come from the next observation, the next idea, or the next person willing to look up and wonder.